choose the pure substance from the list below. The answer should be what? Diamond. How would you answer this question if you didn't know what diamond was made out of? Because I imagine that could be an issue here, right? We didn't really talk specifically about diamond. So maybe you know what diamond is made of, maybe you don't. How might you answer that question if you didn't know what diamond is made of? Yeah.
Go through everything else.
Right, is that what you're gonna go to? Yeah. Yeah, you could go through these other ones that we did talk about: air, milk, seawater, and tea. I think we talked about all of those things as being mixtures of at least two different substances. If you can name at least two different things that make up each of those, then it's not a pure substance. So that leaves only diamond. And what is diamond made out of? Carbon. Carbon. So diamond is actually an element. It's just carbon. All right, this one went pretty well. So we looked at this one in class as well. It's at that second level. But more importantly, we need to know our precision, and that should be 87.20. Because there's that. The 2 is given by the little line, so the next digit is your uncertain digit. All right, what else didn't go so well? This next one. Converting meters to millimeters. So first of all, we should be able to go look at a problem like this and at least eliminate some possibilities. How can we immediately eliminate some possibilities here without even doing any calculations or anything?
Because you know it's going to be 3 away, so 4 and 16 are way out of it.
Okay, yeah, so I didn't think about it that way, but you know that the difference between millimeters and meters is 10 to the 3, if you know that. So it's got to be, it can't be 10 to the negative 4 or 10 to the negative 16, because that's too far away. I was just thinking, you know that millimeters are smaller than meters, right? So it's going to be more millimeters than meters. So that means anything less than 10 to the minus 10th can't be right, because that's less than meter. And then that would mean that a millimeter is greater than a meter. So it couldn't be 10 to the minus 13 or 10 to the minus 16. So if we do all that elimination, then we know the only possible one is 10 to the minus 7th. So that should be the answer. Okay, this is the second one. This one went a little bit better. So what did you guys put for this one that was wrong a lot? Anybody want to admit it? This one. What was the most common? Yeah.
I know I put 13.
Okay.
And,
so you just went the wrong way? Yeah. Okay. I'm guessing that's probably a common mistake. People put the 13 went the wrong way. Yeah. Okay. So something to watch for next time. All right. We've got, this was really, this is the same question as that sort of complicated liquid nitrogen question that we went over in class. You have a certain volume of something of a certain density. What would be the volume that an equal mass of something with a different density take up? So you solve for mass of mercury here by converting that to milliliters, 950, and multiplying by the density. And then you divide that density by 0.789, or that answer by 0.789 to find how much space that ethanol would take up. All right, and this was one from the book. This might have been actually the same as one of the assigned mastering chemistry ones. So you saw the answers here, 32F to degree C. That should be one you could do without calculating. So that would be 0. So even if you forgot the equation, you should be able to get that one. 77K to degrees F, you're going to convert that to degrees C, right, and then to F using that equation. Does anybody want to see that equation in practice? Or you want? Yeah? Okay, let's take a look at it. So let's go K to F. I'll just do it here on the thing. So 77K to degrees Fahrenheit. 77K, we can add 273 to get degrees C. So that's going to be 350 degrees C. And then how do we convert from degrees C to degrees F? What's the order? Is it multiply and then add, or subtract and then divide for C to F? Nobody remembers?
Multiply to that.
What? Multiply then add, right. So we're going to go 1.8 times 350, whatever that is, and then add 32. And I believe you get, oh wait, this should be, sorry, we went the wrong way, right? Nobody caught this? This is wrong. Let's change that. What did I do wrong? I added instead of subtracted. So I got to subtract 273 to get degrees C. So what is that? Negative 196. Is that right? Yeah. Is it? Now I'm uncertain. Yeah, that's right. Okay, so negative 196 times 1.8 plus 32 is going to get us negative 321 degrees F. Sorry about that. Get my head out of vacation mode here. All right, same thing here, and then body temperature. Body temperature in, this is close to body temperature, but you have to still do the equation in this case because it's asking for more significant figures. So we can't just say, oh, it's about 37. C, which would be 310, 310K, right? I don't know. We can look that up. Okay, and then this one was also widely missed. What was the mass of this many platinum atoms? How do you find the mass of an individual platinum atom?
Just look at the atomic mass.
Yeah, the atomic masses are averages of isotopes, that's true. But this isn't talking about any particular isotope. They're also molar masses, meaning that's how many grams are in 1 mole. But we can take them as atomic masses. We talked about that assumption, how we can assume that each individual platinum atom weighs 195.08 because the average is generally going to be correct. So we can take that 195.08, multiply it by this number, 5.1 times 10 to the 21, and that should give us the mass of that many platinum atoms. But that is not in, so what is the mass? What is that? What are the units of that mass then? Atomic mass units, not grams. Since the question is asking for grams, what do we have to do instead?
Use moles.
Yeah, we have to use moles. So let's look at how we do that. That's 5.10 times 10 to the 21. So 5.10 times 10 to the 21 platinum atoms is how many moles? So how do we figure out how many moles that is?
By 6.02 times 10 to the 23.
Yeah, so we're going to say there's this many platinum atoms, and there are, in 1 mole, we have 6.02 times 10 to the 23rd atoms. So we divide those two numbers. I can do that on my phone real quick here. So 5.1 divided by 6.02. And then it's 21 divided by 23. 10 to the 21 divided by 10 to the 23. So that's 0.847 times 10 to the minus 2. Moles of platinum. Or right, 0.00847 is what that is. Sorry, I don't have a scientific calculator, so do it that way. So then we multiply that by the number of grams in 1 mole, which is 195.08, and that should give us our answer. Finish writing this. .00847 moles of platinum times 195.08 grams per 1 mole. And whatever that is, grams of platinum, that should be your answer. So if that were asked in AMUs, we could just use the number and multiply by 5.1 times 10 to the 21. Or if you happen to remember the number of grams in an AMU, it's like, I don't remember. Easier is to just use moles to do that equivalence. And then the bromine ion, Br minus, is element 35. So it still has 35 protons. Anything called bromine must have 35 protons. If it has a different number of protons, it's a different element. What would change the fact that it's a Br minus ion rather than a Br element? What changes there? The electrons. So it would have one more electron than protons. So still 35 protons, but 36 electrons. So other questions about the quiz? All right, then let's move on. The third homework is up. So you can start practicing some of the stuff we're doing today. What we're going to get into today, we're going to talk a little bit about the periodic table. We'll get into all the trends and everything in a later chapter. We're just going to talk in some general terms about ions. And then we're going to get a little bit in the second part of today into naming. And I'm going to have some practice for you to do. Has anybody done naming of compounds before? Previous classes, like sodium chloride versus whatever, like how you name those? Okay, good. So that is that's a really important part of the class. And it's not just because I want you to memorize a bunch of names or something. It's because if we want to talk about chemistry, we have to actually know the language that we're using to talk about chemistry with each other. And so we need those names. And this is a source of trouble for students in this class for the entire semester, unfortunately. So I really want you to focus on getting this now so it doesn't become an issue later. Because the problem is that if we don't get the names now, then later, when quizzes and exams are written, assuming you know those names, they don't go so well. So let's talk about them now. First, a couple things, just classifications on the periodic table. We've talked a little bit about the numbers before, so we know that. Let's categorize metals and nonmetals. Metals are the left side, nonmetals are the right side. What separates left from right in this case? Is it the middle of the periodic table? Now, what is it?
That like little stair step thing.
Yeah, that little stair step thing you see in black. Everybody see that between boron and aluminum, like 5 and 13, kind of stepping downward onto the right there? That's the line where we separate and we say, okay, the things on the left are called metals, the things on the right are called nonmetals. The things right along that staircase, anybody know what we call those? Yeah, metalloids or semi-metals. They kind of, because they're in the middle, they kind of have properties of both. So some properties of metals, you might know, they tend to be conductive. They conduct electricity because of their electronic structure, the way their electrons are arranged. They are malleable and ductile. What does that mean? I don't know what that means. Yeah, okay, yeah, you can shape them, you can bend them, if malleable specifically has to do with hitting with a hammer. If you take metal and you hit it with a hammer, it doesn't shatter, it spreads out, and you can hammer it into very thin sheets that way. Other compounds, nonmetals, that doesn't happen. If you take sulfur or carbon type compounds, or just like rocks, think about a rock, you hit a rock, it doesn't spread out into a thin sheet, it just shatters and crumbles and breaks. And so those nonmetals tend to be brittle, whereas the metals tend to be malleable. Ductile specifically talks about pulling into wires. That you can kind of, same idea, that it's flexible like that, but that you could pull it into thin wires. And you can't do that with the nonmetals. All right, a couple things that you should know about some elements and their charges. The alkali metals. Where are the alkali metals? The far left, group 1A. So another thing to know about the column designations. The old way is what's shown up there, where you see 1A, 2A, and then the ones through the middle there are labeled with B's, and then it goes 3A, 4A, 5A, 6A, 7A, 8A. Some years ago, that was voted to be changed to just straight numbering from 1 to 18 across the top. So if you look at a more modern periodic table, you'll see both numbering schemes, like in your lab notebook here. You'll see the straight numbers across the top, and then the A and B column numbers across the bottom. Either one is fine. You know, we'll see both of them. So column 1A up there are called the alkali metals. An important thing you should know about them: they form 1+ ion. They tend to lose 1 electron to form a 1+ ion. Did you know that already? Some people know that. Okay. But where do you think the alkaline earth metals are? 2A, right next to them. And those are the ones that form the 2+ ions generally. Those are important things to know as we talk about forming ionic compounds. And then where are the halogens? Yeah, halogens are 7A. So let's label these here. This is going to be 1A, 2A, 7A, but specifically that's just the 4 elements, like that, okay? Acetine is radioactive, and we don't really include that in that category of halogens. And then where are the noble gases? Yeah, 8A at the end, tend not to form compounds. Have you ever heard of pnictides or chalcogens? Where do you think they might be? What columns haven't we? Everyone want to take a guess at one of those?
6A and 5A.
Yeah, 6A and 5A. Actually, the opposite. So this one's 5A, and this was 6A, except generally not oxygen. Oxygen's not really put in that category, but sulfur, selenium, and tellurium. You don't need to know those names, but you should know these 3 or these 4 for sure: alkali metals, alkaline earths, halogens, and noble gases. So periods. We had this on the pre-test. I know a lot of people got mixed around, probably just because of how the words are written on the periodic table. But the periods go across, and the groups go down. Why do we call it a periodic table? What is important about that? What is a period, and why is it? Why do we call it that? What's happening that is periodic there? What does it mean for something to have a period? Math folks here. No? It's not the punctuation mark. All right? Then it just means that something that happens regularly over and over again. Something that cycles. And the periodic table cycles because you go left to right, and then when you get back to the left again, you have similar properties again. So that's why we have vertical groups, because those elements have similar properties. And so it's like we have an element of this type, 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 and then we go back to the beginning and we have one like the first one again. So that's why the rows are periods. And in fact, in some formulations of the periodic table, they're seen as actually kind of wrapping around. So you'll see there are some kind of fancy different periodic tables that people have come up with. And a lot of times they have that kind of, if you imagine a three-dimensional one that kind of wraps around itself, that kind of makes more sense because as you go through the elements, you come back to where you started. So we don't need to talk about all that stuff. Let's get into our naming now. So why do we have these naming rules? Well, believe it or not, as much as people tend not to like learning all these naming rules, it's a whole lot easier than the alternative, which is memorizing the specific name for every different type of compound. I don't think we want to do that, right? But that was the situation for much of history. Every time something was discovered, it would get named. And so you'd have things like saltpeter, Epsom salts, laughing gas, grain alcohol, wood alcohol, all these different names that don't really have any systematic tie to the actual chemical formula. Like if I said, what's the formula of grain alcohol versus the formula of wood alcohol? Could you tell anything by those names? Probably not, right? So we need to, is there anything about saltpeter that tells you that it's KNO3, that that's the formula? Probably not. So we don't want to memorize all these individual names. It's going to be a lot more efficient if we could just memorize some rules that always apply to all the compounds and then work back and forth, assuming we know those rules. So we're going to start simple, and we're going to progressively build. There's basically 4 categories that we're going to put things in, compounds in. And we'll start with binary compounds. Now, binary compounds are compounds composed of how many elements? 2, right? 2 elements. There are 2 types of binary ionic compounds. Not chemically they're different, really, but 2 types of how we name them. There's either going to be a type 1 of naming or a type 2. So the first type is the simplest. We have a positive ion that's always written first, and then a negative ion, and we name it accordingly. So let's try a simple one. Like, let's say we want to come up with a compound between sodium and chlorine. And we'll talk about why it's not chlorine in a minute. So that's going to be Na and Cl. So first we have to decide which one's going to be the positive ion and which one's going to be the negative ion. What do you think? Probably know this one, right? Sodium's the positive ion, but why? How could you figure that out if you didn't know it? It's in the first part of the periodic table, and we know that those tend to be +1 type ions. But even more generally than that, everything to the left of that stair step, everything that we call a metal, tends to make a positive ion. There are relatively few examples, and none really that we'll see in this class, of where those elements make negative ions. So if you have something to the left of that line, you can be relatively confident that that's going to be the positive ion. And you can be pretty confident that whatever's to the right of that line is going to be the negative ion. So in this case, we can actually know their exact charges. We know that sodium's going to be +1, chlorine's going to be -1 because of where they are in the periodic table. And then to name them, the cation is named first, and the cation actually doesn't change its name. So Na+ is called sodium. Just like Na neutral, with all its electrons, is called sodium. The positive ion is also called sodium. And then the anion, the monoatomic anion, so where there's just one atom there, chlorine in this case, its name is taken by taking off the end and adding "ide." So instead of chlorine, we have chloride. Example, N3-, what would you call that in an ionic compound? So we said it. If the element of N is nitrogen, right? So if it made a negative ion, what would that be called? Based on that rule. Nitrite. See how that works? So you got nitrogen, and it turns into nitride. Chlorine turns into chloride. Carbon turns into carbide. Phosphorus, phosphide. Sulfur, sulfide. So you can see how that works. All right, so if we complete our name then up here, that NaCl compound is going to be called sodium chloride, as you knew. All right, so let's look at a couple other examples in that category before we go on to the name one. Anything that fits into this type 1 category, where you just have two types of elements, a cation and an anion. And the cation, we know the charge of what it's going to be, or what it is. We just name it that easily. You put the name of the cation and the name of the anion with I. So CaO, what would we call that? Calcium oxide, right? Ca is the plus, is the positive ion. Oxygen is the negative ion. SrF2. Anybody know what Sr is? Sr is strontium. So what would the name of that compound be? What is it? Strontium fluoride. Yeah, thanks. Right. And then what about K2Se? We know K, right? What's K? Potassium. What's Se? Selenium. Yeah. So what would K2Se be? Close. Yeah. Add one more little syllable in there. Yeah, potassium selenide. Potassium selenide. So calcium oxide, strontium fluoride, potassium selenide. All right. Let's get a little trickier. Type 2 binary ionic compounds. This rule comes about because some metals specifically, have an issue where those general names from before are not specific enough. Okay, iron, for example. Iron can be in the 2+ and the 3+ state. You can have two different types of ions. Because this problem comes up, look at these two compounds. We can have FeCl2, which is what happens when we have a +2 iron. We can have FeCl3, which is what happens when we have a +3 iron, because the overall compound has to be neutral. We can't just say iron chloride, because either one of those would be iron chloride. So we have to come up with a way of distinguishing one from the other. And the way that we do that is when we have an ion where the cation can change its charges, we put the charge of the cation in Roman numerals in parentheses. So the rest of the naming is the same, but we add these parentheses to describe the charge of the metal. So that said then, let's give ourselves a little bit of a room here. FeCl2 versus FeCl3. We're going to call them both iron chloride. But we're going to add a number in parentheses to say the charge of the ion. So what's the charge of the iron ion in the first one on the left there? 2. It's +2. And how do we know that it's +2? How do we know that iron in that particular compound has a +2 charge? Yeah, we can't tell from the periodic table because all those ones in the middle have actually variable charges. Anything from 3b to 2b, with a couple exceptions that we'll talk about, pretty much have variable charges. So we have to look at the rest of the compound. We know each chloride is a 1- ion. So that means that if there's 2 1- ions, there must be 2+ on the iron to balance that out. So then this one must be what? The other one? 3. So we've got iron 2 chloride and iron 3 chloride. The biggest mistake I see with these, well, two big mistakes. One is forgetting that that Roman numeral applies to the charge of the metal, not the number of anions, but the charge of the metal. So I'll show you an example. Cu2O versus CuO. What's Cu? You know that one? That's copper. Cu is copper, and oxygen, or O is oxygen. So the O ion is oxide. What kind of an ion does oxide make with charge? Do we know the charge of the oxide ion? Do you guess? Based on where it is? What? Close, -2. The ones, the FClBri are -1. The next ones in 6 are -2. And then the next ones make -3. So oxygen is going to be a -2 ion. So what does that tell us the charge is on copper? Let's first look at this one on the right. If oxygen's -2, what's the charge on copper? Two, yeah. So +2 or 2+. And then what's the charge on copper on the one on the left? Go the other way. 1 is, I guess, what I meant. Sorry. Yeah. So we have to balance out the -2 from the oxygen. If we have 2 copper atoms, 2 copper ions, that means they each need to be +1. So you've got 2 +1s and then a -2, and those balance each other out. So that means that when we name these, what are we going to do with our parentheses? This one's going to be copper something oxide. And this one's going to be copper something oxide. What goes in the parentheses on the left? 1. Because it's copper 1+. Now notice there are 2 of them. That is not what we put in the parentheses. It's the charge that goes in the parentheses. So that's a major mistake that I see people trying to name these. So that means that this other one is going to be copper 2 oxide because the charge on that copper is +2. The other mistake that I see made on these types of problems is mixing up this type with the other type. Remember, type 1 were compounds where we know the charge of the cation. The charge of the cation is always fixed. Type 2 are when there is question about whether or not, or what the charge is. There are some tables in the book that I think will be helpful. Oh, we kind of skipped over that. That's all right. We'll get to that in a second. So if you go to the book, there are some compounds that you should know. So we can get all these here. I missed the heading, so we'll make our own heading here. All right, so here are the ions with fixed charges, type 1. Now, most of these are pretty easy to figure out from their group number. All the 1As, all the 2As. It's these last 4 that are a little weird. So you can remember all the 1As are +1, all the 2As are +2, but then you've got 4 more to remember. Aluminum, zinc, scandium, and silver. Those 4 also only have 1 charge, but they don't like fall nicely into the group like that. So I would Just try to remember those last four. Everything else that you see, all the other metals in the middle, in all those B rows, with these couple exceptions, have variable charges. So those are all going to be the type 2 metals, where you have to use the parentheses to specify the charge. The common anion charges are a little easier. We'll put those in there too. You should know these as well. They all follow their group number pretty well. So you've got the halogens, 7A. You've got oxygen and sulfur at 6A. And then you've got nitrogen and phosphorus in 5A, so -1, -2, -3, going from right to left. And actually, they're not on this table. This table is just some, but things like selenium and tellurium can also fit in there in those same columns. All right, let's try this, and then we'll take a little break. So, CuCl or CuCl2. We already talked about copper as being Cu. So what are the names of these two? What's the name of CuCl? Copper 1 chloride. And what about CuCl2? Copper 2 chloride, right. There is another older naming system that's described in these notes. I don't want to get into it because I think it's just going to be confusing. But if you want to know, if you ever hear these names like ferric chloride and ferrous chloride, or cupric chloride and cuprous chloride, that's other ways of naming these higher and lower charge type compounds. That's not necessary for this class, so I'm just going to skip over it right now. Other examples, oops, before we get to the other types of compounds, let's look at the polyatomic ions. So sometimes you'll see compounds that look like this. And these are still ionic compounds, but they're made up of these grouped type ions, these ions that have multiple atoms inside them. So first we've done the binary compounds, which is monoatomic. Now we're looking at the polyatomic ions. Have you learned these ions before? Seen some of these things? Things like ammonium and hydroxide and all that kind of stuff? Well, guess what? If you got them, good. If not, got to do it here. So let me show you the table of what you need to know. So we'll have it for the rest of class today as we start working on this. Let's see if we can, yeah, there we go. So pull this out of your book. This is table 3.5, so you can see it in your book as well. Here are some common polyatomic ions. You need to know the formula and the charge for all of these. Now, hopefully, most of these you've learned before in your previous chemistry class, so it's just a matter of kind of brushing up, maybe learning a couple that you didn't learn back then. But this is absolutely something that you need to know to be able to name these compounds. So you need to know the name and the charge and the formula for each of these. So you need to know that nitrate is NO3 and its charge is -1. You need to know that sulfite is SO3 and its charge is -2, and so on. So we'll use this chart today. By next week, we'll have a quiz, and you'll need to know these for sure as part of the whole naming thing. So if it's not something you've learned before, it's been a long time, you can't remember them, make yourself some flashcards or just kind of carry this little table around and learn these names again, because we'll use them a lot throughout this semester. All right. That said, let's take a little break. We'll come back. We'll just finish up these last categories of naming in the discussion part, and then we will do some practice. So we talked about these different naming rules. Let's talk about the final categories of names, and then we will get into some practice. So I think it's probably more helpful to just try it than going through all the names. But the final category are the binary covalent compounds. And these are compounds that don't have any metals in them. And so instead of the bonding being ionic, meaning you have positive and negative ions, you have what's called covalent bonds where the electrons are shared. We'll get more into the details of what covalent bonding means in later chapters. For now, the key is looking at that line on the periodic table. If you've got one from one side and one from the other, or you've got polyatomic ions, then you're using the rules we already talked about, the polyatomic ion naming rules. If you only have nonmetals and they're not grouped into polyatomic ions, then we're all on the right side, and then we're using these rules, which are the covalent compounds. Now, most people actually like these rules the best. It's the most, I guess, straightforward. You're just going to say the name of the first element, the name of the second element with "ide," like we did before, but then you're going to put these prefixes in front of each one to say how many of each they have. So, and the only other rule then is you don't put mono for the first prefix at the first element. So CO is carbon monoxide, monooxide because there's one oxygen. SiO2 is silicon dioxide. It really should be monosilicon dioxide, but we dropped that mono off the first part. So if you're not familiar with those prefixes, they are mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and hexa for 6. We're not going to see compounds, there's more than 6 here. So mono, di, tri, tetra, penta, hexa, and then named accordingly of whatever. So here are some different compounds of nitrogen and oxygen. Some of them have common names like nitrous oxide or nitric oxide, but we're going to focus on these systematic names. How do we name exactly the types of atoms? So based on those rules I just told you, these are covalent compounds, what we call N2O. Yeah, dinitrogen monoxide. And if there's 2 O's, like monooxide, we usually drop one of those O's. So this becomes whoops, but right, dinitrogen monoxide. And then we've got nitrogen monoxide, nitrogen dioxide. What about N2O3? N2, what's the N2 part? Dinitrogen, and then what's O3? Yeah. Dinitrogen trioxide. And then N2O5, that will be dinitrogen what? Pentoxide. Again, we dropped that last letter so that we don't have 2, that last A for penta, so we don't have 2 vowels in a row. Okay, before we go to the practice, let's just do a couple that P4O10 is actually P2O5, is often named as P2O5. So let's name these. What would P2O5 be? I'll type it. P2O5, what do you think? We want to give it a shot? First, we have to categorize it. So that's really, I think, where most people go wrong in getting these names. You have to decide where is it. Is it ionic or covalent? And then what type is it? So is P2O5 all ionic or covalent? How do you know? Covalent? How do you know?
Because it's all.
Yeah, everything's over to the right of the staircase. P and O are both on the right, so this is going to be covalent. That means we name it that last type, that covalent type. So now that we know how we're going to name it, what's the name? Yeah, diphosphorus pentoxide, right? Diphosphorus pentoxide. Okay. In fact, let's make ourselves a little flow chart. So we'll say first, we decide, is that ionic or is it covalent? If it's ionic, we go over here. If it's covalent, we go over here. If it's covalent, we're done. All we need to do is write the names. So we would write, I'm just going to write prefix blah, blah, blah. So you know the idea. Di, mono, that's when we use those. If it's ionic, we have another decision to make. Do we know the charge on the metal? Is it a fixed charge where it's always the same? In fact, we shouldn't say no. We should say, is it a fixed charge? If it is, then we know that our name is going to be the metal and the nonmetal ide. If it's not a fixed charge, then we have metal with parentheses, metal ide. We should also say or the polyatomic ion. So it's either the nonmetal ide, like chloride, sulfide, or the name of the polyatomic ion, like sulfate or nitrate, that kind of thing. All right, so now that our flowchart is right there, let's use it for this next one, NB2O5. Is that going to be ionic or covalent? Ionic? How do you know? Yeah, metal and a nonmetal. So that puts us over on the left. Does it have a fixed charge or a variable charge? Everybody find NB? Niobium? Yeah, that's number 41. So right in the middle of what we call the transition metals. So that's a variable charge, which means we're going to name it with the parentheses. So that's going to look like niobium, parentheses, oxide. What do we put in the parentheses? What's the charge on niobium? 5, right. We know each oxygen is -2. There's 5 of them, so that's a -10 total. If we've got 2 niobiums, each has to be +5 to balance out for -10 total. So that's going to be niobium 5 oxide. All right. Let's skip that lithium one because that one's actually pretty tricky. We'll get back to that one and look at this bottom one. Same question. Ionic or covalent? TiNO34. Is that ionic or covalent? You want to give a guess? Ionic, yeah, how do you know? Right, titanium, Ti is over there, and so we know we've got metal and non-metal. All right. Is titanium have a fixed charge? Ti, that's number 22. Is that a fixed charge metal? It's not. It's all in the mess with the rest of them. So this is going to be a similar name as part B. So titanium blank, and then what do we put for the anion? What's NO3? Anybody remember that one? I know I just gave you the list, so yeah. What?
Nitrous oxide.
Close. That would be what it would be as that would be N2O as a covalent compound, but this is an ion, so this is the nitrate anion. And anybody know the charge of the nitrate anion? We can go back up and look at our table for now. For this week, we can look at the table. We find nitrate right here, NO3 minus, so that's a 1 minus. So if nitrate is 1 minus, what must the charge on titanium be? 4, right? Because there's 4 1 minuses, so that must be 4 plus. All right. Let's jump back to C then. What's tricky about Li2O2? First of all, is it ionic or covalent? It's ionic because we've got metal and nonmetal. Does lithium have a fixed charge? Is lithium one of the ones that always has the same charge? It is. So lithium is +1. That means we're in that first category over on the left. Is it just lithium oxide then? This is the problem. It's not lithium oxide. Why is it not lithium oxide? So the charge of lithium is known. What's the charge on lithium have to be always? +1. What is the charge on oxygen if it's oxide? -2. But that doesn't fit, right? You can't have 2 +1s and 2 -2s in a compound. So that tells us that in this particular case, O2 is not oxide, but rather it's a polyatomic ion peroxide, which is O2 2 minus. All right. That's an unusual one, but it's one to watch out for. If you've got 2 oxygens together like that, it could be peroxide, which is 2 minus on its own. So that makes sense. We've got lithium plus, and there's 2 of them. And then we've got O2 2 minus, which is peroxide. So the name of this one, it's still that first type. The name will be lithium peroxide. All right, you can also go the other way, where we start with the formula and go to the name, or start with the name and go to the formula. The only difference is we have to make sure to balance the charges. A neutral compound must always have the charges add up to 0. So as much positive as you have, you need the same amount of negative. That means for vanadium 5 fluoride, what I like to do if I'm not sure about these, or one thing you could do starting with this, is you write out the ion with its charge, so V5 plus, and then you write out as many of the other ones as you need to balance it out. So what's the charge on fluoride? -1. So we need 5 of those to balance out the 5 plus, right? And that means the formula of vanadium 5 fluoride should be VF5. If we go down to the next one, B, that's a covalent one. Those are easy. Dioxygen difluoride is just O2F2. The covalent ones are nice because they tell you exactly how many of each thing you need. You don't have to worry about balancing out charges. I'll let you try those last couple. And then let's go to this sheet. So the sheet here, if you started off at the beginning, it asks you to either write the formula for the name or the name for the formula. And you've got a bunch to do. Some of them we haven't quite talked about yet, like the acids. That's fine. You can either skip over those or just read this and then figure out how to do it. You can look at them at home. Where is it? Here. For those of you who don't have an electronic thing to access the notes on, I'm going to set this back up to the polyatomic anion. So you can use that for our polyatomic ions. There's actually one cation here, ammonium, NH4+. So you can use that as reference. It's up to you how you want to work on this. Work on your own or work with your partner. And then when you get to this part where it says physical characteristics, you can skip that because we don't obviously have this stuff here to look at physical characteristics. But those are also more practices with names and formulas. You can make it all the way through this packet, and you can start actually being able to do it without looking back at the rules and without looking back at these tables. You're really going to be in pretty good shape with your naming because this is a whole lot of stuff. So go ahead and start working on this. You can work alone. You can work together. Whenever you feel like you got a good sense of it, I would say after a couple pages or so, you don't have to stick around, but I would recommend that you do. This is your time to ask questions and all of that. So go for it.